today I'm going to discuss about laser engineered net shaping lens of blown powder additive manufacturing. As I mentioned earlier, like in my last presentation, lens has advantage of when compared to powder bed additive manufacturing. It has high deposition rates and it can repair mold surfaces and it can repair parts where there is a build height is a constraint, which is not possible in powder bed additive manufacturing. But it has some disadvantages when we compare with powder bed additive manufacturing techniques. The surface roughness what we obtain from through lens is not as good as the one we will get through powder bed technologies, and the dimensional accuracy is also not precise enough. So today we are going to discuss about the process description and the process variable which are going to affect the final part quality, and the journals or the papers who discussed about the varying the process parameters and the microstructures of the final build parts. So as we can see two nozzles which are dispersing the powder in the previous last few seconds of video, and the laser is melting that sub powder on the substrate, and this is how they fill the powders into the nozzles powder feeder system, and thus how the laser builds the parts layer by layer. Those are the final parts which are obtained through lens process, and you can see the surface finish on the parts is not as good as the parts what we obtain through powder bed technologies, SLS or DMLS. Uh, this is how lens is used for repairing the parts instead of building it. So the process variable which affect the final part quality are laser power, laser wavelength, feed rate, linear velocity, layer thickness, and the material what we are using. It can be the material of the substrate what we are using, or it can be the material what we are feeding into the system. Uh, as I mentioned in my last presentation, by increasing or decreasing the laser power and feed rate and scanning velocity, it may have effect on the surface roughness of the part quality and the dimensional accuracy. So for my first research study, I've chosen the paper of laser rapid manufacturing of stainless steel 316L and Inconel 718 using FGM. They varied the FGM functionally graded materials by varying the composition, and the final study of this research group is to study microstructure evaluation and mechanical properties of the final parts what they made through lens, and those are the authors, and it was published in International Journal of Optics. And the scope of study is to study the to characterize the microstructure and to study the micro hardness properties. So it uses a laser power of 400 watts, and the substrate they are using is laser carbon steel, and the scanning velocity of 500 mm per minute, and the spot diameter of 1 mm, for the powder feed rate of 4.3 to 4.4 grams per minute, and the particle size of the two powders they have used are in the range of 45 to 90 micrometers. So in this, the research question over here is, uh, they want to investigate the microstructure characterization and the hardness, micro hardness along the graded direction, and the one over here is the how they varied the compositions. In this is in the transverse direction and one in longitudinal direction. So they started with 0% 316 LP powder with 100% inconel, and gradually when we go through layers by layers, it gradually decreased. And here you can observe the microstructures over here. FGM is the one using this composition. You, A, B, C comes under functional graded materials of FGM. You can observe the columnar dendritic growth in the microstructures, except at the edges. Here you can observe the columnar dendritic growth was transformed into cellular dendritic growth or equiaxial dendritic growth, which have a lot of effect on the micro hardness of the parts. And when we use this composition FGM2, uh, the columnar dendritic growth is not as does not appear as dominant as you observe in the first three microstructures. You can observe a lot of variation, columnar, cellular, and equiaxial dendritic growth. So how those microstructures, what I'm talking about, columnar, cellular, dendritic growth, how it affects the mechanical properties. Here you can see that the micro hardness of the FGM1 in longitudinal section drops, and suddenly it increases, it continuously increases. This is because up to 40 to 50 volume percentage of inconel, it decreases due to ferritic and austenitic phase in them. And when the volume percentage increases of when the inconel volume percentage increases, the hardness increases because of the increase of elements of chromium and molybdenum, which results in increase solution hardening effect in the component. So, and you can observe the micro hardness in the FGM2 samples in normal section and the longitudinal transfer section. And the transfer section gives you the highest hardness values. This is because of columnar dendritic growth, whereas the normal one contains cellular dendritic growth. So the next research paper, what I've studied for this presentation is process efficiency measurements in lens process. So the scope of study of this process is to measure the process efficiencies. The process efficiency might be laser energy efficiency, melting efficiency, and deposition efficiency, which is directly related to the process variables what I talked in the second slide of laser power, flow feed rate, and scanning velocity. So they have used they have used the lens 750 from Optimec, and they have studied two types of products here: S13 tool steel powder on S13 tool steel substrate and copper powder on S13 tool steel substrate. So here you can observe how the laser energy transfer efficiency is varied with a heat input. So from this figure, it can be concluded that the powder mass flow rate or the laser power has no effect on the energy efficiency. So we may think, as I said, they are studying on the copper powder deposits, and people and we know that copper has high reflectivity rate, so which results in low energy absorption. But this result shows that copper has nothing to do with the low energy if copper has nothing to do with the absorption of laser power. So the only thing which laser energy efficiency is dependent on the substrate material. If they use copper as substrate materials, we may get different results over here. So the other process efficiency what they focused is melting efficiency. You can observe the melting efficiency between different traveling speeds uh, and different flow rates. So for higher flow rates and higher scan speeds, the melting efficiency increases with increase in laser power, and it is also dependent upon the laser energy efficiency. We can see the laser efficiency into power over here, and the one graph to my right is powder mass flow rate with constant powder mass flow rate but different but using different scan speeds, and you can observe that by increasing the scan speed the melting efficiency increases, and they concluded that melting efficiency increases with increasing power, flow rate, and travel speed. And I didn't find a process model what we use in like common process equation what we use in powdered bed technologies, but I thought this would be relevant for this lens process that are studying the laser transfer efficiency and melting efficiency. So laser transfer efficiency in their equation it shows that it is related to the powder power and the flow rate and the time of deposition, but the study in previous paper has shown that it doesn't there doesn't laser power and flow rate doesn't have any effect on the laser energy transfer efficiency. So these were the reference what I've used.